go ahead and begin.
You're welcome. It's very exciting. I was wondering.
How's everybody?
Good.
Good? Good. Okay, so today we're going to start chapter 2. I do have a broken clicker, so you're going to be patient with me as I shuttle back and forth to change slides. So my goal today is to get through half of chapter 2. We are going to start a new note sheet. So we're going to be doing some calculations, so just know and be ready for that. Okay, so linear kinematics. So kinematics, both linear and angular, are an important part of this textbook. We study things from a linear standpoint to start off with, and then we get all the way to chapter 6 before we look at things from an angular standpoint. So kinetics means studying an object or body with respect to space and time. So whereas kinetics, which we'll get to in chapter 3, deals with forces. So we'll have chapters on both linear kinetics and angular kinetics. First of all, what is motion? So process of changing position. So two things we need for motion. We need time and we need space to move through. So those are two of the things that we measure in sports. If you think of how many sports scenarios are decided by questions such as how far. Okay, so think of how many sporting events are decided by the question how far. How far can someone throw, or how far can someone jump, whether a high jump or a long jump. And then the other question that's common in sports is how fast. Okay. So what is the peak velocity or speed, and what is the average velocity and speed? This chapter we'll go through a lot of practical scenarios where we calculate those variables and answer those questions in terms of how far and how fast. So if we put both linear and angular motion together, we get general motion. So usually when looking at a body or object as it moves, we can pick out parts that are linear, and we can pick out parts that are angular. And so it depends on what you're looking at and what portion or segment of a body or object that you're viewing, whether the analysis is done in terms of linear or angular. But typically we see both examples with movement. So linear motion is also referred to as translation. So as defined here, all points on a body or object move the same distance in the same direction at the same time. So a couple of different types of linear motion or translation includes rectilinear and curvilinear. So rectilinear motion is straight line motion. So for example, think of a line drive in baseball, kind of like a frozen rope type of trajectory. That's rectilinear. Or think of a cyclist moving along a flat section of road. That would be rectilinear. Curvilinear, on the other hand, involves a constant change of direction with a body or object. So this would be an arch in motion. So think about maybe like a football punt. A typical football punt has a rising phase and then a falling phase. So the overall trajectory has more of a curved pattern. And with a football punt, you may have a total air time of 3.5 seconds. So a projectile, which is something traveling through the air, that's only under the influence of gravity and ignoring air resistance, will spend half the time traveling up and half the time traveling back down. So an object is either slowing down in the positive direction or it's speeding up in the negative direction. So here's some examples. So an ice skater gliding along a flat section of ice here, as in figure skating, would be rectilinear motion. What is this sport? I don't want to misname it. Yeah, that's it. So gliding along a lake here would be another example of rectilinear motion. This is an exciting one, ski jumping. Has anyone ever tried that? Okay, so that'd be curvilinear, and you can see the pattern there. And then this old school picture that I found would be diving in a curvilinear way. So there's an arch to the path of motion. Okay, so let's contrast that with angular motion. So angular motion is rotary motion. So motion that occurs about an axis. So the joints in our body represent axes. So if you remember from kinesiology, we have movement through planes. So sagittal, frontal, transverse, diagonal. And the joints in the body represent the axes. So the axis has a 90-degree relationship to the plane of motion. So if we're flexing the shoulder joint or flexing the elbow joint through the sagittal plane, movement in the sagittal plane revolves around the frontal axis. So curvilinear motion is how our bodies move. So our bodies consist of a series of segments that are connected by joints. And so it's that accumulation of angular motion across multiple joints that transfers into linear motion. So imagine a baseball athlete throwing a baseball. They have a transfer of angular motion, or we could even say angular momentum or angular energy that goes all the way from the legs across the torso to the throwing arm, eventually being released, and the path of the ball would represent linear motion. So do you see how we have a transfer from the angular motion that we generate through our bodies into linear motion as we transfer all of that angular energy into a ball or other object? So we see this all the time going on in sports with hitting, throwing, striking, or swinging type activities. It's angular motion that we generate through our bodies that transfers into linear motion as we complete the skill. So a couple of examples that we see here. So isn't Griffey awesome? I don't think he was ever on PEDs, at least never tested positive, but man, how much power is that? So in any case, what we see here is a transfer of angular motion into curvilinear motion of the ball. So general motion. So this is a combination of linear and angular motion. So here you have the greatest sprinter of all time, greatest human sprinter of all time, Usain Bolt. Anybody know the greatest racehorse of all time? Arguably, Secretariat. Okay, so that's Secretariat. So just most actions, if we look at the joints, is angular, but the overall movement of the body is linear motion. Okay. So a cyclist, again, provides another great example where you have angular motion of the pedals, but if you look at the object as a whole, it would be linear motion. So depending on what you're looking at, depends on whether the analysis is linear or angular. So a lot of times it's easy to break things down into different components and then put them all together into one analysis. Okay, so getting into linear kinematics here. So first couple terms, displacement and distance. So both of these involve a change in position. So they're both defined as a change in position. They're a little bit different. So displacement is a vector, whereas distance is not. So distance is a scalar type of quantity, scalar. So with a vector, we want to know two things. Do you remember what they are? Yes, magnitude, and what else? Yeah, direction. So with displacement, we want to define how much and in what direction. So you're comparing the starting point to the ending point in a straight line. Whereas distance is defined as the total length of the path traveled by a body or object. So, for example, if Bryant runs one time around a 400-meter track, what would his displacement be by definition? So, in other words, the starting point is the same as the ending point. So displacement would be? Zero. Yes, 0. Why would it be 0? So it's a straight line change in position. So if the starting point is the same as the ending point, then displacement is 0. Okay, but of course, the distance, the total length traveled, would be 400 meters. So sometimes displacement and distance are the same. So if we're talking about a 100-meter sprint, there's really no change in direction. The starting point and the ending point would apply equally to displacement and distance. So in that case, they'd both be 100 meters. As soon as you have a change in direction, displacement and distance are going to be different. So as soon as a body or object makes a turn or changes their trajectory, displacement and distance are no longer going to be the same. So just remember, one is a vector and one is a scalar quantity. So a lot of you who've maybe been hiking in the mountains, and I've been on hikes before where to get to the top of the mountain, you're just going along these switchbacks all the way to the top. Okay, so you sometimes wish it would be easier if you were a bird and could just fly straight to the top. So this illustrates the difference between displacement and distance. So displacement, as soon as you have a change in direction, displacement is going to be less than distance. So in this case, the distance, the way that you feel would be a lot different considering distance versus displacement. Okay, so here's another application. I want you to take a look at, this is a motion analysis of the bar path for a bench press. So with a motion analysis system like we have downstairs, you put a reflector over the tip of the barbell. And so this is looking at from a sagittal view, so looking at from the side with the path of the barbell that you're able to track with a motion analysis system. And so you have 3 different scenarios here. Novice subject with 245 pounds. Doesn't seem like a novice, does it? So that'd be, relatively speaking, would be a novice. And then you have 2 strength athletes. So Bridges with 463 pounds at the 1980 World Series meet here in B. And then you have Bill Kazmaier, who a lot of people consider the greatest strength athlete of all time, with 605 pounds in 1979 at the Strength Research Center in Auburn, Alabama. And so what you have are the downward path of the bar and then the upward path of the bar. And you notice it's not like a Smith machine. With a Smith machine, what would it look like? Like that, right? Okay, it's different. Okay, what do you notice that's different about we could say the relatively novice person? Yes, 245 pounds is not, from a recreational standpoint, that would be pretty advanced, but elite strength athletes, what are you noticing is the difference between this versus these 2 guys? Especially this over here.
On the
up, he's on this side of the downward.
Yeah. So the down and up are flip-flopped, right? Okay, so what would be the advantage of, and there's a lot of technique application from this in doing a bench press this way, and especially this way if your objective is to lift a lot of weight. So you have to imagine that the shoulder joint is probably, the shoulder joint wasn't marked with this analysis, but the shoulder joint is probably somewhere back here, behind the path of the bar. So back here. So what's the strategy here with Bill Kazmaier with 600 pounds? What's he doing there on the lift up? This has a lot to do with torque and moment arms. So what he's doing is the chest, so this would be the bottom where contact with the chest is made, right here. And then what he's doing is bringing the bar immediately back closer to the shoulder joint, which lessens the moment arm of the resistance. And we're going to get to this in chapter 5 in the discussion, but it essentially makes the weight easier to lift if you have the bar directly over the shoulders versus further away from the shoulders. So you can try it yourself. Even with this is the case, this is not an efficient lifting pattern because he or she is coming down, making contact with the chest right there, and then the weight is drifting a little bit away from the shoulders because the up phase is further out, away from the shoulders, which is a leverage disadvantage, right? Because you're increasing the moment arm of the resistance, the distance from the resistance to the shoulders. Yes?
Is that why some people have like that really big arch in their back when they're bench press?
I think that's a leverage factor, yes. So that would probably shorten the distance that the bar has to travel to complete the lift. So that's a whole other factor, but definitely relevant. Yeah, so the practical application here is when you come down to the chest, contact with the chest is made, and you want to think about kind of an upside down J curve. Can you see how this is kind of an upside down J in getting from the chest back to the starting point? You're not only pushing straight up, but where else are you pushing? You're pushing back. So up and back is the proper coaching cue for a bench press, because then you're getting the weight right in line with the shoulders on this. So just a couple of applications there. Okay, so let's get to velocity. So displacement is defined as a change in position. Change in position without respect to time. So point A to point B. So when we get to velocity, we're progressing, and the question is not how far, in other words, point A to point B, but how fast we go from point A to point B. So it's the rate of change in position. The rate of change in position. In other words, how much displacement we are covering in a given period of time. So as we talked about for the 100-meter sprint, distance and displacement are the same. The difference between displacement and distance can also be applied to velocity versus speed. Okay, so velocity is equal to displacement divided by time, whereas distance is equal to, whereas speed is equal to distance divided by time. So there's a little bit of difference. Velocity is a vector, speed is not. So I just want to play this video clip. It's about Usain Bolt there. And so this is on the science of Usain Bolt. This is a little bit of an older clip. Usain Bolt had his last 100-meter race at the 2017 World Championships in London. His world record was set in 2009, so 8 years apart. It's unfortunate, in his last race, he was third at the World Championships, so he was unable to, it was one of the few times he ever was was defeated, but in the 100 meters. But so he's been retired for a little while.
It's a race people still talk about, analyze, celebrate. The men's 100-meter sprint at the 2008 Summer Olympics in Beijing. Jamaica's Usain Bolt tearing up the track as he sails over the finish line in world record time. Crowned the world's fastest human, Bolt betters his own mark a year later at the World Championships in Berlin, blazing to victory in 9.58 seconds.
I want after Olympic Games, people should say, wow, when they turn their TV off, sit back in their chair for a minute, think about what just happened. That's what I'm looking forward to. I want to just wow people.
While fans admire his speed and showmanship, it's the biomechanics of Usain Bolt that intrigues mechanical engineers like Annette Hassoy, a professor at MIT who has been supported by the National Science Foundation.
Usain Bolt is unique in that somehow he is able to both get the top acceleration and maintain the top speed.
Bolt is amazing because someone his size isn't expected to move so well and so fast. But the exceptional combination of his size and his strength makes Bolt unlike any champion before him. At 6 feet 5 inches, Bolt is several inches taller than most of his rivals. His longer legs give him a naturally longer stride. Other elite runners average 44 steps to run 100 meters. Bolt averages just 41 steps.
His stride length is enormous, so every time he takes a step, he covers a tremendous amount of ground.
But because he is larger, Bolt has more mass than other sprinters and needs more strength, more force to move his body. With each step, Bolt generates enormous force against the ground. The ground applies that force back, propelling Bolt forward. Bolt moves more mass than other runners, and he moves it faster.
The amount of force that you can give to the ground depends partially on your technique, but mostly on how much strength you have in your muscles.
Bigger muscles generate more force, so Bolt, like all sprinters, trains hard at the track and in the weight room.
I work really hard now because I'm not really a fan of the gym, but you have to do it to get that strength, that power you need to get out of blocks.
Strength isn't just how big is the muscle, but it's how big is the muscle and how much force can it produce while it's moving.
How the muscles function during motion is part of the research conducted by Samuel Hamner, a mechanical engineer at Stanford University, who has also received support from the National Science Foundation. Hamner collects data in a motion capture room using infrared cameras and sensors and creates dynamic simulations, information that can help treat movement disorders and also help athletes optimize their performance.
If we can understand what the functional roles of these muscles are, it might help Usain Bolt change his training or better understand how he can become faster.
Hamner explains that as Bolt sprints down the track, more than 30 muscles in each leg work together in complex coordination during the 2 phases of the running gait, the stance phase and the flight phase. In the stance phase, Bolt has at least 1 foot on the ground.
When your foot first hits the ground, you're actually slowing down, you're braking your body, and you're using muscles in your thigh, like called your quadriceps, to actually slow you down and support your weight while you're coming into contact with the ground. In the second half of the stance phase, you start then accelerating your body forward again, and this time you're using some different muscles, your calf muscles, to push yourself up and accelerate you forward as you then lift off into the flight phase.
In the flight phase, Bolt has both feet off the ground. His hamstring muscles on the back of the thigh pull the leg down before his foot hits the ground again. The flight phase showcases Bolt's superior stride length. He's in the air longer, flying farther with each powerful step.
So there's actually kind of very precise actuation of each of the muscles when you're running. If you're off by a few milliseconds when you're generating these forces, you'll fall over or you'll injure yourself. So it takes precise timing of the electrical signal that comes from your brain to your muscle to create that force.
If Usain Bolt is at his biomechanical best, he could turn in another spectacular time in London's Olympic Stadium.
For me, it's just the strength and the length of my stride, everything comes together, which makes it look so superb.
And when it all comes together, it's a thrilling race to the finish line.
Okay, so how many steps for Usain Bolt?
41.
41 versus a normal sprinter is,
44.
yeah, 44. And then I thought it was interesting how they discussed the braking phase, which is a rapid eccentric muscle action followed by a rapid concentric action. So it's the rapid coupling of muscle action. So a muscle not only has to relax quickly, but it also has to contract quickly. So he's storing energy in his muscles during the braking phase, during the deceleration phase, and then he's releasing all of that energy during the subsequent concentric push-off from the track. So speed obviously is an advantage in almost every sport. So I thought I'd come up with a football example here. So all of you with your cell phones, you have like a stopwatch function on it. Pull up your stopwatch function. I want you to take a time for me. So this is Tyreek Hill way back when he was playing at Oklahoma State. So this is one of his, it was either a kickoff or a punt return for a touchdown. And what I want you to do is time how fast he goes from this position right here where he just caught the ball and is just starting to initiate movement until he crosses the goal line. The unique thing about this run back is that it's almost a straight line. So it's a really good example of straight line movement, point A to point B to the end zone with displacement. So I'm just going to go down here. And so on 3, I'm going to hit the play button. Okay, so 1, 2, 3. Sorry. Okay. Let's do that one more time. I was hoping I could stop it right when he crossed the end zone. Let's do that one more time. Okay, hang on. I'm going to stop it right when he catches it. Okay. So everybody reset your clock. Okay. So on 3. 1, 2, 3. See if you can stop your clock right when he crosses the end zone line. There you go. It's almost like he was breaking the tape in track,
And
right?
that's what
Did you
he
see
did.
that lean that he did? Okay. All right, so what were some of the times you got? About 10 seconds, a little over 10 seconds. Pretty fast, right? Okay. All right, so we're going to use some of the trigonometry stuff that we were looking at from chapter 1. So looking at the field, caught the ball right here. Okay, it's about the 4-yard line and ended right here. So if you look at that run, it was one of those unique scenarios where there was good blocking, almost a straight shot right to the end zone. So this is our resultant displacement. And so we can draw a couple lines. So we can make our right triangle. Okay. So doing some quick estimates, just looking at the video where things were at. So it was actually the 3-yard line where he caught the ball. So if we make this right triangle, can you calculate what his resultant displacement was? So if it's a right triangle and and this is theta. Theta is not really relevant in this problem, but if you have two of the sides, not the hypotenuse, you can solve for the hypotenuse. Remember the Pythagorean theorem, right? And put that into your calculator and see what you come up with. So you can have either one, a squared, either way, either one can be a or b. You'll get the same result. So the hypotenuse is equal to the square root of a squared plus b squared. So what did you come up with for your resultant displacement? 103. Okay. So 103 yards. Okay. And then I want you to, so the answer to A here, what was the resultant displacement? That'd be 103 yards, right? And then what was the average velocity based on your time measurement? So whatever time you got, and there was probably a little bit of variability, but whatever time you got, you divide 103 yards, which is from here to here, that was our resultant displacement, divided by your time measurement to get yards per second. Yards per second. You should come up with, I don't know, 9.5 yards per second. That's with football gear on, right? Pretty amazing. Okay, so the difference between speed and velocity, velocity is a vector, so displacement divided by time. Speed, on the other hand, is a scalar quantity, so it's equal to distance divided by time. So we're not defining direction, just the total distance divided by the time interval in question. Okay, so here's a figure showing over the years the progression in the world record for the 100-meter sprint. So if we look at different athletes here, Ben Johnson and Carl Lewis, this is the 1988 100-meter final at the Seoul Olympics. And Ben Johnson won the gold, was later disqualified for PED use, but it was a world record. And subsequently, Carl Lewis was given the gold medal, and the 992 was the world record. So we can see a couple of athletes here. Ben Johnson was way ahead in terms of sprinter races, 979 versus 992. So then we go to 1999, Maurice Green also ran a 979. Then in 2001, Maurice Green again, 982. That was Tim Montgomery in 2002, 978. And then you started to have the dominance of the Jamaican sprinters. Beginning in 2005, Asafa Powell, 977. And then at the 2008 Olympics, that you saw that race in that video, Usain Bolt at 969. And then a year later, at the World Championships in 2009, that was where the 959 came from. So it's really interesting. So track and field, there's a minimum reaction time that you have to be over in order for the start to count. So the official IAAF rules state that if the athlete initiates movement in less than 1/10 of a second after the gun has fired, the athlete is false started. So obviously you're probably thinking, what? Well, that's very debatable. Okay, but that's the rule, that's the way it is. So they figure that the time for someone to initiate movement from the time the starting gun fires should be no less than 1/10 of a second. So you can see up here, RT stands for reaction time. So you look at all of these outstanding performances and you can see the different reaction times. There's Tim Montgomery, that was the closest one right there. So that's a little over a tenth of a second, 4/1000ths of a second over a tenth of a second. Asafa Powell, Usain Bolt. So Usain Bolt, one of the things over the course of his career that he was constantly trying to improve on was his start. So part of the issue with him was his height. So how tall from that video?
6'4".
6'5", whereas the other athletes were significantly shorter than that. So it's difficult to get a 6'5" frame out of that crouch position quickly. So as you'll see in 2009 when he set the world record, his reaction time had significantly dropped. So he had corrected that problem. Everything came together perfectly in one race, and then you get 9.58, which no one has been even close to since that time, and we're 2023. So information like this is really useful for coaches. So you can see sprinting has 3 parts. It has a start, it has an acceleration phase, and it has a maintenance of maximal velocity phase. So you can see any issues with the start, being able to quickly initiate motion, the reaction time for that. And then what's neat about this figure is you can see the intervals for each 10-meter segment. So you can see the acceleration phase. So if we take a look at Usain Bolt here, over the first 10 meters, his time was 1.85 seconds. And then we're going from 10 to 20 meters, 1.02 seconds. So you can see each 10-meter segment is gradually getting faster because the time is less. So gradually building speed, still building speed, still building speed until we're somewhere around 70 to 80 meters. He was still covering those 10-meter segments in 0.82. Now you take a look at some of the other sprinters. Like Ben Johnson was considered an incredibly powerful sprinter in terms of his start and acceleration phase. His problem was hanging on all the way to the end. So can you see that? His segments, a lot of them were pretty close to Usain Bolt. His fastest 10-meter segment was 0.83. Usain Bolt was 0.82. The thing about Usain Bolt though, 0.82, 0.82, 0.82, 0.83. So that's what made him so great, is that once he got everything moving, he was somehow able to hang on to that maximal velocity longer than anybody else. And that's what produced the phenomenal times. Whereas, take a look at Ben Johnson over here. So he gets up to his top speed somewhere between 50 and 60 meters. So you accelerate, you reach a top speed, and then the idea is to hang on to that top speed as long as you can. So you can see kind of, but then kind of falling off towards the end there. So they're still giving maximal exertion, right? Obviously. Well, if you actually watch this race, the last 10 meters, he was kind of showboating, goofing off. But up to that point. So is it their intent to slow down? Why were they slowing down then? Why is the last 10 meters slower than the middle of the race? What's going on there? This is more of a physiology question. Fatigue, yes. So there's many mechanisms that produce fatigue. So probably a limitation in the phosphagen system. So even an elite athlete, these superhumans that can move their body so quickly, their training is directed towards this maximal velocity phase, a lot of them. So Usain Bolt's training, he had no problem with maintenance of maximal velocity, so his muscles were very efficient, storing and releasing elastic energy. His issue was more on his start. Take Ben Johnson for the other hand, his issue was more maintenance. He would gas out after about 60 meters, and so his training was more directed towards how can I hang on to this top speed. Carl Lewis was just an overall probably one of the greatest of all time. He also was a long jumper, an elite long jumper. His long jump was second all time, and still is today behind Mike Powell. So over 29 feet for Carl Lewis. So he was not only an elite sprinter, but also a long jumper. I'm wondering if he could have dunked from maybe the 3-point line. I would have liked to. If you can jump 29 feet, you definitely have the distance to do it. You'd still have to have the height, though. Okay, so this is an interesting figure from your textbook because you have a contrast of Usain Bolt's world record, still stands today, set in 2009, versus his very last race, the 2017 World Championships in London. And he got the bronze medal. So Justin Gatlin and Christian Coleman finally edged him out. And it's really, you ought to look it up on YouTube, because it's kind of an emotional moment because Justin Gatlin and Christian Coleman had never beaten him before. And here he is going out. And Christian Coleman, he was kind of reaching his peak at that time. So what we have here, figure 2.1, we have the elapsed time. So the elapsed time at 10 meters, 1.89, 20 meters, 2.88, and so on. At 90 meters, 8.75, and then a finishing time of 9.58, as well as the elapsed time from his last race in 2017. So if you take a look at the elapsed time for each of those segments, definitely for a sprinter, he was starting to show his age. Still extremely gifted and elite, but not quite where he was in 2009. Over here, rather than elapsed time, we're given the interval time. So the fastest 10-meter segment ever covered by a human on record was during this race. So from 60 to 70 meters in his 2009 world record race, he covered that in 0.81. So nobody's ever done that in a 100-meter race. So 0.82 and 0.83 is phenomenal. That's typical of what you see with these other elite guys, but nobody had dipped down into that 0.81. So that was phenomenal. And so what you see here is the average speed for each segment. So we're talking about 10 meters divided by the interval time. So if we divide, for example, 10 meters by 0.81, you're going to get 12.35 meters per second for that 10-meter interval. So at any given time during that 10-meter interval, he was moving at 12.35 meters per second. So you can see that's his top speed right there, and then he's able to hang on really well. And notice from 2008, his last 90 to 100 was 0.9, or he was kind of goofing around a little bit, knew he had the race won, showboating a little bit. He didn't do that in 2009, 0.83 for that last segment. And so then you get this phenomenal 9.58. I'm wondering if anyone's even going to touch that record for, I don't know how long. You never know, though. Somebody might come along. But so what I want on this one, let's take a look. 3 parts. What was Usain Bolt's average speed for the entire 100 meters in 2009 and 2017, respectively? So speed, again, equal to distance divided by time. Distance divided by time. So you'd have a distance of 100 meters. And then you'd have his finishing time from 2009 and also 2017. you get for 2009? What was his average speed for the entire 100 meters? Let's go two significant digits.
10.44.
Yeah, 10.44 meters per second. So slightly slower in 2017, but still over 10, right? Slightly over 10. What'd you get for 2017?
10.05.
Yeah, 10.05 meters per second. So that's pretty straightforward. Any questions on that one? Okay, so the next one, B. How fast did Usain Bolt run the first half of the 100 meters in 2009 and 2017, respectively? So that's pretty easy. That's just a matter of just looking at the elapsed time. And so if you go to the elapsed time, the first half up to 50 meters, you can see Usain Bolt 5.47 seconds for 50 meters in 2009, and 2017, 5.64 seconds. Okay, so that's pretty straightforward. So the second half of that question, and what was his average speed for this segment of each race? So again, just looking at distance over time, so distance of 50 meters divided by 5.47, distance of 50 meters divided by your 5.64. So what are some of the numbers you're coming up with? Probably 9 something. What'd you get, Ashley?
9.14.
Yeah, 9.14 for 2009. Okay. What about 2017? What was his?
8.87.
8.87. Okay, so then to extend on that, now we're going to look at the last half of the race. So how fast did Usain Bolt run the second half of the 100 meters? So he's already moving. So this is going to be significantly faster because we're not starting from zero velocity. So how fast did Usain Bolt run the second half of the 100 meters in 2009 and 2017 respectively? And what was his average speed for this segment of each race? So then you've got to simply look at what his final time was, right? And you're going to subtract what? If it was 9.58, what do you need to subtract from that?
5.47.
5.47 will give you the time. And then you can just divide that into 50 meters. Same thing over here, 2017, 9.95 minus 5.64 divided into 50 meters for that. So just curious, what was his average speed for the second half of the 2009 race?
4.1.
I was thinking more, maybe like 12, really fast.
12.17.
What was it? 12.17 meters per second. So things are a lot faster if you start something already moving. So any questions about these tables, how to read those, what calculations mean? So I think it's useful to know what's going on at different segments throughout the race. It can kind of break down where an athlete strengths and weaknesses are. Hey, all right, so we're coming up on a different event here. Now it's not just point A to point B in a straight line. Now we have a change of direction. So Wed Jan, so 400-meter world record holder, Rio Olympics 2016, and almost broke 43 seconds. So let me like to play this. This is kind of amazing because if you know anything about track and field, we've got some track and field athletes. He was running in lane 8. Is that like an ideal spot?
Yeah, totally.
So he set the 400-meter world record running way out in lane 8. And then you've got these other guys, LaShawn Merritt, and this other, I can't remember his name, but these two right here were the favorites for the gold medal. And he kind of got into that final and just, I don't know, just running like a scared. It was amazing to watch. Okay. So this is him out here.
That was awful.
Incidentally, he also holds the world record for the 300 meters, which that's not raced very often, but you see the two favorites right there, and he's just gradually leaving them. Right there, so yeah, that's another one where I don't know if it's going to be broken for a while. Okay, so because we have a change of direction, we can't use velocity because velocity is with displacement. So we have to use speed because there's distance, so the total length traveled by the body or object. Okay, so this is a figure showing that race. And there's a couple different ways of looking at speed. So in this race, we have each section, 0 to 100, and so on, all the way up to the last section where you're in the home stretch. And the 100-meter split for each of those parts. Now, the first section, you're going around a curve, right? You're in that curve right away, and then you have the back stretch, and you're starting that already moving, so right, 9.78 down the back stretch. Okay, so around the far curve, 10.5, and then the home stretch, 11.99. Now, why is it 11.99? How many of you have ever ran one time around the track as hard as you can go? How do you feel in that last? Yeah, so that's another, we're getting into that physiology, right? So the acidosis is starting to kick in, right? So your cumulative time is here, like before with Bolt. But here's what's interesting that we didn't see with Bolt. We have broken down the number of strides. So how many strides for 100 meters for Usain Bolt again?
41.
41. So we can see here, those numbers are pretty close. So Wade Van de Kerk has a pretty long stride. And then the total strides. Going all the way around the track, we get 163 strides. And then the stride frequency. So the number of strides per second for each of those 10-meter segments. So for which he was pretty consistent. The last 100 meters, his stride frequency was slowing down. So he was taking, in other words, that last 100 meters when he's really struggling. But if you look at his form, didn't it look effortless? The way he was running, even the other guys that got second and third, it just like effortless. Like you wouldn't even be able to tell they're in pain just from their form and holding their form all the way through. So his stride frequency slowed down quite a bit in that last 100 meters. So he's taking fewer strides per second. So here we have the length of each of those strides. So in meters. So his stride length was the longest down the back stretch. So 2.63 meters is what he was covering on each of those strides down the back stretch. And turns out that's where he was running his fastest split. So one of the ways we can look at speed, other than distance divided by time, we can take stride frequency, which is strides per second, multiplied by stride length, which is meters per stride. And then if you multiply those two together, the strides cancels out and you're left with meters per second. So you can get pretty close results either way. So let's do some application here. So what was the average speed of the first 100 meters using the 100 meter split time? So what I'm asking for is 100 meters, so around that first curve, 100 meters divided by 10.76. So let's go again, let's go two significant digits. So what'd you come up with? Should be
9.29.
Yeah, we'll say 9.29 meters per second, okay? So then on part B, what we're going to do is calculate the same thing, only what we're going to use is stride frequency and stride length. Okay, so we're going to take that first 10 meter interval, and here you have the stride frequency, so strides per second, right? And then multiplied by the average stride length is 2.34. So if you take these two numbers, 3.98 multiplied by 2.34, so we're taking the average stride frequency multiplied by the average stride length. So an average times an average, it's not going to be exactly what you got with the first problem, but it should be pretty close. So what'd you get?
9.31.
9.31. So you got 9.29 meters per second versus 9.31 meters per second. So this is just another way of calculating the same thing. So in order to get those numbers exact, you'd probably want a smaller time interval. So anytime you multiply an average by an average, you're going to start to vary from what it actually was. Okay, so what was the average speed for the entire 400 meters using the cumulative time? So for this one, we're looking at distance, 400 meters, right? And then multiply, or divided by 43.03 to get the average speed. So he still holds the 300 meter sprint record and the 400 meter record as well. But I was really impressed with it. Anybody watch that Norwegian 400 meter hurdler? 45 something is the current world record, 45.9. And then the gal from the United States, the 400 meter hurdler from the United States, she runs faster than some of the flat 400 meter runners. So it's McLaughlin, right? So pretty impressive. Okay, so in your textbook, there's these speeds that are noted for different ball sports. So we take a look, fastest reported speeds. Something that's going to be useful in this class is being able to convert meters per second to miles per hour. So it's kind of hard to, because we're in the United States, we don't use the metric system as much, so we relate to miles per hour a lot better. So for example, if Corey's facing a pitch that's coming at 100 miles per hour, that's 44 meters per second, almost 45 meters per second. But 100 miles per hour is more meaningful to us because that's what we're used to seeing most of the time. So we look at a couple of these numbers here. So guys soccer, 82 miles per hour on a penalty kick. So how do you react to that?
You don't.
That's quick.
You don't react, you just.
Yeah. Softball, 104 miles per hour. So I'd like to play, there's an interesting video that I found comparing the difficulty in hitting a fast pitch softball with baseball. And so they take a couple of comparisons. So let's go there next. Let's see, right here.
Bless you.
Let's see. Here it is right here.
It's all about myths and legends on this episode of Sports Science.
You ever tried to hit a softball pitch, Corey? Like a fast pitch one? Yeah. Looks different from what
Some people think that hitting a baseball is the hardest thing to do in sports. Is that true? We found someone who wants to put that myth to the test. Meet Jenny Fitch. Jenny is a 6-foot-tall Olympic gold medalist and NCAA Pitcher of the Year. She believes that hitting a softball is harder than hitting a baseball and is here in our lab to prove it. To start, we wanted to compare the force with which a baseball and a softball arrive at home plate. The harder it hits, the harder it is to hit.
And we have our strike force plate behind here to actually measure the load or the force that the ball generates when it impacts. Basically, all you have to do is have the pitch break through these two beams and hit that plate, and we'll be able to collect the force that's generated.
First up, baseball. Cal State Fullerton flamethrower Adam Jorgensen will see how much force his 95-mile-per-hour fastball creates. The 95-mile-per-hour fastball generates 2,411 pounds of force when it hits the strike force plate. Now, let's see if the softball generates more or less force than the baseball. Jenny's pitches will provide unprecedented data, so we can determine once and for all which contains more force, baseball or softball.
You just broke it. Look.
Coming in, they told me that I was gonna throw against some scientific gear, and my goal was to come in here and break it. That's what we did.
Jorgensen's missiles generated an impressive 2,411 pounds of force. Jenny's first pitch broke the machine. We're going to give round one to Jenny. With their high-tech equipment smashed to bits, we decided to test baseball versus softball by bringing in a live research subject, Arizona Diamondbacks prospect, Brian Byrne. Brian hit .310 last season in the minor leagues. First, he's going to face our baseball flamethrower. Brian has no problem hitting 95 miles per hour baseball pitches. He's a pro. Now, it's Jenny's turn, and Brian has to hit off a pitcher like none he's ever faced, and from a lot closer. Let's just hope she goes easier on him than she did on our gear. rules are no surprise. A baseball hitter facing a pitcher standing 60 feet 6 inches away and throwing 95 miles per hour has only 395 milliseconds to react to the ball. Jenny, standing only 43 feet away and throwing 70 miles per hour, allows the hitter only 350 milliseconds to react. So a softball batter has less time to react. And that's not the only disadvantage.
We did a lot of studies on what makes it difficult to hit a pitcher, and one of the things that makes it difficult is the visual. Baseball hitters typically are used to seeing a pitch come from a certain area, so unless they've seen a lot of pitchers that come from down under, they're gonna have a difficult time with that.
Our Vicon House of Moves motion capture technology allows us to break down the pitching motion of Jenny Finch in order to illustrate exactly why it's more difficult to hit a softball than a baseball. This is not a computer simulation. This is Jenny's actual pitch. The softball pitch may look casual, but it packs a punch. Jenny's shoulder is a fulcrum, and her arm a 3-foot-long lever. With massive rotational inertia, she rockets the ball over 70 miles per hour.
I think her long arms kind of
The
help.
baseball's falling high to low path
Getting
makes a
velocity.
last instant swing adjustment easier. Because of gravity, a batter can quickly drop his hands and hit a descending ball. For softball, the low to high trajectory makes adjustment difficult. It's much harder for a batter to raise his hands than it is to drop them, making a rising softball pitch a unique challenge.
What do you think? It's just different. A lot different. What's tough? What's the biggest single difference? I think it's just the angle. And, Jenny was throwing some balls that rise.
To admit that hitting a baseball is the hardest thing to do in all of sports, shattered.
Now I gotta test it with the roll this Chapman told me.
Yeah. Yeah, Aroldis Chapman. Is that 106? Something like that?
105.
Okay. All right, so practice problem number 4. Okay, so a baseball fastball often has a horizontal velocity of 44.7 meters per second. So 100 miles per hour or 146.67 feet per second. The horizontal displacement of the ball from the point of release, so 60.6 inches, but you can see here the ball is released a little bit in front of the mound, or in front of the rubber there, is going to be 58 feet, 17.68 meters. How long in time does it take for the ball to reach home plate? So tell me, what is your velocity equation? Velocity is equal to what? Displacement divided by time. So to solve this problem, we're looking for the time. How long? So you just swap the velocity. You take displacement divided by velocity to calculate the time. So it'd be displacement, which would be 17.68 meters divided by the velocity of 44.70 meters per second. And you should come up with a value pretty consistent with what values were given there in the video. So a little under 0.4 of a second. Something like 3.3, what'd you get? 0.395 seconds to react. So okay. So similar problem, hockey goalies, another athlete that has to have tremendous reaction time. So during an ice hockey game, Phil had 2 shots on goal. One shot was 5 meters away at 10 meters per second, and one shot was 10 meters away at 40 meters per second. Which shot did Brian, the hockey goalie, have a better chance of blocking? So it's just comparing times here. So you have displacement divided by velocity, and then you're comparing the times. So one is 0.5 seconds, right? What's the other one?
1.
0.25. So the other one is half that. So half a second versus a quarter of a second. So the one for 10 meters at 40 meters per second was the faster one, or you had to react quicker. Okay, so almost the last practice problem here. So a swimmer is traveling with a velocity of negative 3.2 meters per second. So why do we have to define direction then? Because velocity is what? Velocity is a vector, so we define direction. So there's a positive velocity and a negative velocity. So negative 3.2 meters per second, how far does the swimmer travel in 3 seconds? So we're looking for how far in terms of displacement. So this is just practice working with that equation. So if you multiply the velocity by the time, you come up with, what is it, negative 3.2 multiplied by 3 is negative
9.6.
negative 9.6 meters. So just practicing rearranging that equation to get the variables that you want. Okay. All right, so we went through displacement, which is a change in position. We went through velocity, which is the rate of change in position. Now we're going to acceleration, which is the rate of change in velocity. So these concepts, displacement, velocity, and acceleration, just gradually build on each other. So acceleration, or average acceleration, is calculated in this way. You have your final velocity minus your initial velocity divided by the time interval. So you want to know those two things. So this is for average acceleration, which is different than instantaneous. So instantaneous is just, it's a momentary measure. The moment you assess it is what you got, whereas this is over a longer interval of time. So as the time interval gets increasingly smaller, you're going to be increasingly greater in terms of your acceleration, because a smaller time interval would be associated with the instantaneous or peak value versus the average value over a longer period of time. So you have potentially 6 different scenarios, and the reason you have this is because acceleration is a vector, and so it has direction to it. So in this column we have direction, so the defined direction of motion, so positive or negative. Over here you have 3 different outcomes. You can either be speeding up, so in other words, your final velocity is greater than your initial velocity, speeding up. You can be slowing down, okay, where your final velocity is less than your initial velocity. Or you can have a constant velocity. So your initial and final velocities are equal. So mathematically, what you're going to get is if you're moving in the positive direction, so you decide what direction is positive at the outset. So we said usually to the up and to the right is traditionally defined as positive, down and to the left is negative. So if you're moving in the positive direction, speeding up in the positive direction, you're going to get positive acceleration. So the next one, if you're moving in, you define the direction as positive, but you're not speeding up or slowing down. So final velocity is equal to the initial velocity. What's acceleration going to be? You're not accelerating, right? So it's going to be, it's going to be 0. So same thing here, moving in the positive direction, but slowing down. In other words, you're decelerating. Negative acceleration is deceleration. So slowing down in the positive direction. So same thing would apply down here, only now you're moving in the direction specified as negative. So moving in the negative direction, speeding up in the negative direction gives you negative acceleration. So this is, the top half of this is easier to, I guess, conceptualize versus the bottom half. It all has to do with the math, which is why we do the practice problems. So you'll see how this works. But negative direction, not speeding up or slowing down, 0 acceleration. Moving in the negative direction, slowing down in the negative direction gives you positive acceleration. So negative times negative is what? Positive, right? So mathematically it works out. But it all has to do with your direction of motion and whether you're speeding up or slowing down.
In this class, does change of direction matter for acceleration?
It will, yeah. You may have, you don't have very many problems like that. It does matter, but usually if you're initiating motion from a stationary start, like a 100-meter sprint, the motion that you move into is typically defined as positive. Makes it a lot easier. Okay, so next practice problem. Sean is running a 100-meter dash. So when the starter's pistol fires, he leaves the starting blocks and continues speeding up. So we'll say the direction of motion is positive. Speeding up until he reaches his top speed of 11 meters per second. Okay, so that's at 5 seconds into the race. He's reached his top speed. He holds this speed for 2 seconds. So from seconds 5 to second 7, okay, so at second 5 he's at 11, and then we have 2 more seconds pass. So from seconds 5 to second 7, he's traveling at 11 meters per second. So if velocity is not changing from second 5 to second 7, what's acceleration? It's still 0, right? And then gradually slows down. So we saw that trend where despite maximal exertion, they're doing their best to hang on, but he's slowing down till he crosses the finish line 10.5 seconds after he started the race. So 3 different questions here, and we can just answer these. You already answered one. So what was Sean's acceleration from 5 to 7? 0 meters per second squared. So remember your units. What was Sean's acceleration during the first 5 seconds of the race? So remember your formula, acceleration is equal to final velocity minus initial velocity. What's his initial velocity? 0, sitting in the starting blocks, okay? So 0. So you're gonna have final velocity of 11, because that's what it is at 5 seconds, 11 meters per second minus 0 meters per second divided by your time of 5 seconds. Tell me what you come up with there.
Can you repeat? It's 11
Uh-huh.
meters per second
Yep.
minus, what was the initial?
So it's 0 because he's starting block. So it's essentially 11 meters per second divided by 5 seconds. And what'd you come up with in meters per second squared?
2.2.
2.2, 2 significant digits?
0.
0 meters per second squared. So, and then, like we've calculated several times, average velocity for the whole race, you'd take 100 meters divided by 10.5 to get that one. Okay, so we're starting into the section on projectiles. Okay, so let's talk about acceleration due to gravity. So it's acceleration, it's meters per second squared. What's the number? Yeah, -9, because gravity is a force that directs things straight down. So it's a negative direction. So if we were to do a lab, and I'm not sure I could get approval for this, but if we were to drop something off of a tall building, like that building over there, the liberal arts building, we drop something off the liberal arts building. And so we have somebody at the bottom measuring the time that object is in free fall. So ignoring air resistance, that object is going to speed up at a rate of negative 9.81 meters per second squared. So uniform acceleration, ignoring air resistance. So we haven't got to air resistance yet. That comes in chapter 8. But if it's a still day and we can ignore air resistance, we can predict how fast and how far that object will be during its time of flight. And so if we measure that object 1 second after we drop it, we can say that object has a velocity of negative 9.81 meters per second. And why is that? Because that's what acceleration means, right? It's the rate of change in velocity. So for every second that object is in free fall, it's going to be increasing its velocity by a factor of negative 9.81. So after 2 seconds, the velocity is negative 19.62 meters per second. How do we know that? Because 2 seconds times negative 9.81 is equal to 19.62 meters per second. So after 3 seconds times negative 9.81 meters per second, negative 29.43 meters per second. And then if we just, for the sake of example, if we say it's in free fall for exactly 4 seconds, the moment before it hits the ground, negative 9.81 times 4, going to be traveling at negative 39.24 meters per second. So there is such a thing called terminal velocity that really isn't relevant to biomechanics because we don't fall that far or analyze objects that are falling that far. We can also analyze the distance or displacement an object covers per second in free fall. So here's our equation for final vertical position. So if we consider the point where we drop it is 0, so that's our initial vertical position, we can use this equation to come up with these numbers you see here. So if that object or body is falling for 4 seconds, we can use this equation to calculate in 4 seconds with a constant gravitational acceleration, we'll have a displacement of negative 78.48 meters. So why is this negative? Because what direction is the object falling?
Down.
Falling down, right? So displacement has to be negative. It's a vector quantity. So just give this a try. Let's say, just ignore negative 44.15. That's what you should come up with. But I want you to see if you can calculate. So 1/2 negative 9.81 meters per second squared. So in other words, put 0.5 times 9.81, negative 9.81 into your calculator equals, and then multiply that by, let's see, so at this point it's been falling for 3 seconds, so what's 3 squared? 9. So then multiply that number by 9, and you should come up with negative 44.15 meters as your answer. You do the same thing with any of these other ones. Okay, so that's how far, yeah, in that time. So y, in this case, would denote its final vertical position. So you could do the same thing with 4 here. So 1/2 0.5 times 9.81, and then you'd multiply that by 4 seconds. What's 4 squared? 16. So you'd multiply that by 16, and you should come up with negative 78.48 meters. So is there any question on how that works with gravitational acceleration? So how are we doing on time? 3 minutes. 3 minutes? Is that it? All right, well, there's more I wanted to cover today. Okay, so what part of projectile motion is affected by gravity? So in this case, if I was to, this is the author actually, that's the author that's tossing that ball. But, and I don't know where, maybe somewhere in campus, because he's somewhere in upstate New York is where he's located, but he's got this nice wall with this grid. But so he's tossing this ball, and this ball has both horizontal and vertical components. So what component of projectile motion is affected by gravity?
Not the vertical.
Just vertical, right? So gravity has no effect on the horizontal component. Air resistance affects the horizontal component, but we're ignoring air resistance at this point. So we're just considering the vertical component. So we could say that this ball, once it leaves his hand, this ball is slowing down. At what rate? What's the rate of change in velocity during the ascent? You know what it is. What's the number? Negative 9.81 meters per second squared. It's slowing down in the positive direction. So as soon as it leaves his hand, it's slowing down in the direction, in the positive direction. So eventually it reaches the peak of its flight, and then it starts coming back down. So now it's speeding up in the negative direction. So what's the rate of change in velocity as we speed up in the negative direction? Negative 9.81 meters per second squared. So the acceleration is the same whether we're slowing down in the positive direction or speeding up in the negative direction. So we can look at different sports. This is the very last slide today, I promise. Okay, so high jump, obviously you want enough horizontal to get over the bar. Okay, so you don't want to go straight up and straight back down, or you're not going to clear the bar, but we want a little bit of horizontal to get over the bar, but mostly vertical. Okay, a three-point shot in basketball. How many of your old basketball coaches said you need to put more arch on your shot, right? So that's important. A hammer throw, right? So you have horizontal and vertical components. So each of these arrows represents the vertical velocity versus the horizontal velocity during the flight of the hammer. What do you notice about the vertical velocity as you go from the release to the peak, and then as you go from the peak to the landing point? Yeah, it slows down and speeds up, negative 9.81 meters per second squared. What do you notice about the horizontal component, though?
Stays the same.
Stays the same. Why? Because if we ignore air resistance, gravity has no effect on the horizontal part. So the horizontal release velocity will be exactly the same as the horizontal velocity just before it lands. Questions? Okay. All right. Thank you. Have a good weekend.